Airplanes do not stay in the sky because of their engines. They stay in the sky because air is moving over their wings, and that leads to a consequence that is easy to miss. If that motion stops, even briefly, the airplane cannot remain in the air. There is no pause. There is no hovering. There is no backup state where it simply waits. By the end of this video, you will understand exactly how flight actually works and what really happens when that motion is lost. Most people picture an airplane being held up by its engines. That intuition comes from what is visible. The engines are large. They are loud. They produce thrust that can be felt during takeoff. And when engine power is reduced, the airplane descends. So it is reasonable to assume the engines are what keep the airplane in the sky. That assumption is not entirely wrong. The engines are essential. They provide the forward force that allows the aircraft to move through the air. But they are not what creates lift. Lift is the upward force that counters the airplane's weight. And that force comes from somewhere else. It comes from the wings interacting with the air itself. The important shift happens here. The engines make the airplane move forward, but it is the movement through air that allows the wings to hold the airplane up. So the real system is not engine equals lift. It is motion through air to airflow over the wing to lift. Once that relationship is clear, the focus moves away from the engines and onto something that cannot be seen directly, the airflow over the wing. A wing generates lift by changing the direction of the air it moves through. As the airplane travels forward, air flows over and under the wing. The shape of the wing, called an airfoil, is curved so that the air above it speeds up and the air below it is deflected downward. That change in airflow creates a pressure difference. Lower pressure above, higher pressure below. The result is an upward force. That upward force is lift. A simple way to feel this is to hold a hand out of a moving car window and tilt it slightly. The air pushes the hand upward. The same physical interaction is happening at a much larger scale on an airplane wing, but that interaction depends entirely on motion. If the airplane is not moving forward through the air is not being redirected. And if the air is not being redirected, lift is not being produced. There is no gradual transition to a stable state without motion. Lift decreases rapidly as speed decreases because it depends on dynamic pressure, the force created by moving air, which increases with the square of velocity. So the first constraint is established. No airflow, no lift. The engines now take on a more precise role. They do not create lift. They provide thrust, a forward force, that keeps the airplane moving fast enough for the wings to generate lift. A useful comparison is a bicycle. A bicycle stays upright not because something is holding it up, but because forward motion allows it to remain balanced. Remove the motion, and the system no longer works. The airplane operates on a similar dependency. Forward speed is what allows the system to function. From here, flight can be understood as a continuous exchange between energy states. The airplane has forward velocity, motion through the air, and it has altitude. Those two are constantly traded. Pilots describe this as the airplane falling forward. That phrase does not mean the airplane is dropping. It means that the aircraft is always converting forward motion into the lift needed to remain level. Even in steady cruise, lift equals weight and thrust equals drag. But the system is active. The airplane is constantly maintaining the conditions required to stay aloft. This leads to the next constraint. There is a minimum speed below which the wing cannot produce enough lift. That speed is called the stall speed. A stall is not an engine failure. It is an aerodynamic condition where the airflow over the wing is no longer able to produce sufficient lift. This happens when either the speed is too low or the angle of attack, the angle between the wing and the incoming air, becomes too steep. In either case, the airflow separates from the wing surface and lift drops sharply. Aircraft are designed with this limit in mind. Every part of the system, wing size, shape, and operating procedures, assumes the airplane will remain above this minimum speed. And this is not just a design choice, it is a structural requirement. The airplane cannot function below that speed, so the entire operation of the aircraft is built around maintaining it. That includes the instruments, which measure airspeed. It includes the autopilot, which uses those measurements to maintain stable flight. And it includes pilot training, which emphasizes keeping the aircraft within a safe speed range. All of these systems share a single assumption, that the airplane always knows how fast it is moving through the air, because that speed is not just a performance parameter. It is what allows the airplane to remain in the air at all. And this system becomes more constrained as the airplane climbs higher. At high altitude, the air becomes thinner, meaning its density decreases. Air density is the amount of air mass in a given volume, and it directly affects how much lift a wing can generate. With less dense air, the wing must move faster through it to produce the same lift. So the minimum safe speed, the stall speed, increases. At the same time, another limit is approaching from the opposite direction. Aircraft also have a maximum safe speed, often defined in terms of Mach number, the ratio between the aircraft's speed and the speed of sound. As altitude increases, the margin between these two limits begins to shrink. The minimum speed rises, the maximum speed falls. And eventually, the airplane operates inside a narrow band where both limits are close together. This region is known as coffin corner. In some aircraft, the difference between stalling and exceeding maximum speed can be only a few knots. A knot is a unit of speed used in aviation equal to 1 nautical mile per hour. So even in normal cruise, with all systems functioning, the airplane is not surrounded by a wide safety margin. It is operating inside a carefully maintained range of speed, where small changes matter. The system remains stable, but it is precise, which means if that airflow is lost, even without anything visibly failing, the airplane has nothing left to hold it up. In June 2009, an Airbus A330 was flying from Rio de Janeiro to Paris. The aircraft was at cruising altitude over the Atlantic Ocean. The engines were operating normally, the aircraft structure was intact, and the airplane was maintaining level flight. Then the pitot probes iced over. Pitot probes are sensors mounted on the aircraft that measure airspeed by comparing air pressure from forward motion to static atmospheric pressure. When ice blocks them, the aircraft can no longer reliably determine how fast it is moving through the air. On this flight, all 3 airspeed readings became unreliable. The autopilot disconnected. The flight control system reverted to a degraded mode. The crew was now flying manually, without reliable airspeed information. They responded by pulling back on the controls. That increased the angle of attack, the angle between the wing and the oncoming airflow. Lift initially increased. Then the airflow over the wings began to separate. The aircraft entered an aerodynamic stall. A stall is the condition where the wing can no longer produce sufficient lift because the airflow has detached from its surface. The airplane was still moving forward. The engines were still producing thrust, but the airflow over the wings was no longer generating lift. The airplane was intact. The engines were running, but it was no longer being held up by the air. The aircraft began descending, not as a dive, as a sustained fall. For several minutes, the airplane remained in this stalled condition. The nose stayed high. The descent continued. The crew did not recognize the stall in time. The aircraft impacted the ocean, and all 228 people on board died. The same dependency appears in a different form in February 2009. A Bombardier Q400 was approaching Buffalo, New York. The aircraft encountered icing conditions. Ice began to accumulate on the wings. A stall warning activated, a system designed to alert the crew when the aircraft is approaching the critical angle of attack. The correct response is to reduce that angle and increase power. Instead, the captain pulled back on the controls. The angle of attack increased further. The airflow separated. The aircraft stalled and entered a descent it did not recover from. All 49 people on board and 1 person on the ground died. The warning system functioned. The engines were available, but the airflow over the wings was no longer sufficient. In December 2014, an Airbus A320 was flying from Surabaya to Singapore. A recurring system fault led the captain to reset circuit breakers. This action disabled parts of the flight control system. The autopilot disengaged. The aircraft entered manual control in a degraded mode. The airplane climbed sharply. As it climbed, its speed decreased. The angle of attack increased. The stall warning activated. The aircraft entered a high-altitude stall. It did not recover. All 162 people on board died. In October 1994, an ATR-72 was flying in icing conditions near Chicago. Ice accumulated beyond the levels the aircraft was designed to handle. The shape of the wing changed. The airflow behavior over the wing changed with it. Lift characteristics were altered. The aircraft experienced a sudden loss of control. It entered a rapid descent and crashed. All 68 people on board died. Across these cases, the pattern is consistent. The engines continue to operate. The aircraft structure remains intact. The systems may partially function or fail in different ways, but the outcome is the same. The airplane no longer has sufficient airflow over its wings to generate lift. And when that condition is reached, the system behaves exactly as designed. Lift decreases. The aircraft descends. There is no alternative mode. There is no way for a fixed-wing airplane to remain in the air without that airflow. After these events, changes were made. Pitot probes were redesigned to be more resistant to ice. Flight crews received expanded training in recognizing and recovering from stalls, especially at high altitude. Procedures for handling unreliable airspeed were clarified and reinforced. Aircraft systems were updated to improve redundancy and provide clearer warnings when sensor data disagrees. These changes addressed how the system fails. They improved detection. They improved response, but they did not change the system itself. A fixed-wing aircraft still depends on continuous airflow over its wings. It still cannot generate lift without forward motion. It still requires the aircraft to remain above a minimum speed to stay in the air. That has not changed because it cannot be changed within this design. So the core condition remains. Flight exists only while the air is moving over the wing in the right way. And that airflow is not something a passenger can see. It is inferred, measured, managed, but never directly observed. Which leads to a final question. If the system depends entirely on something invisible, and that invisible quantity can be misread, interrupted, or degraded, how certain can any system be that it is still there? Because an airplane does not fall when something breaks. It falls when the air stops doing what the system assumes it always will.